Thank you for taking the time today to join us for our advanced manufacturing presentation of full process multi-axis automation. My name is Rob Kobielski, hosting today's event, and I'm joined by two of my colleagues, Jeff Stelling and Mike Belanger of AMS 360. AMS 360 is a CAM specialized partner of Autodesk based in Windsor, Ontario. Now, Windsor is well known to be an automotive superpower, but the region's manufacturing stronghold is far more expansive, with specialties across several sectors including aerospace, injection molding and mold tool manufacturing, materials, robotics, stamping, tool and die, and more. We have three speakers lined up for today's presentation, and I'd like to take a quick moment to introduce them. Mike Belanger comes from the tool and mold manufacturing industry. While working as a senior machinist on 5-axis machines, he was also responsible for training new recruits. Over the last 5 years with Autodesk, and now with AMS 360, Mike works closely with customers to optimize their digital manufacturing solution. Jeff Stelling is an applications engineer and post-processor specialist. He joined our team after 20 years in the manufacturing industry working as a tool and die maker and CNC machinist. Jeff adds extensive programming experience of 3, 4, and 5-axis CNC machines and leads our post-processor development. As for myself, I'm 20 years into my career as well, having focused primarily in manufacturing and technological education. Today's presentation is a combined effort that leverages each of our industrial experiences and domain knowledge. Having a quick peek at today's agenda, we can see that the front-end focus will be on applying automation to 3 scenarios with considerably different workflows. Each of us will program a complex model of varying size and shape and discuss critical programming considerations for which automation will have to satisfy. On the second half, we're going to shift the focus to the programming script itself with some tips and tricks for building your own automation from scratch. I hope you find this to be a good use of your time, and I appreciate your attendance today. Before we kick off the first case study, I'd like to take a quick moment to discuss why we're here. CAM programming optimization has been an integral part of subtractive manufacturing practices for quite some time. Most often applied via macros and templates, users would find themselves with considerable time savings versus manually driving the software. In fact, it is fair to say that many companies have already found themselves with a level of automation for roughing and perhaps even finishing of plate work or other simple features. However, there's been very little success in fully automating the finishing of complex free-form shapes. Today, we will discuss some of the best practices in creating a robust and reliable automated solution using the built-in tools of Autodesk PowerMill. I should mention that although this presentation highlights an automated approach to mold tool blocks and components, it is intended for CAM programmers of all products and facets of the industry. So why are we taking on this initiative? The manufacturing industry pressures we're seeing today is increased global competition, a skilled labor shortage, aging workforce, and disruptive business models. On the positive side, we have a lot of opportunities: infinite and inexpensive computing power, digitalization, and of course, automation. The question the manufacturing community is asking: what can I do to stay competitive in the face of this disruption? To which Autodesk and key partners have asked ourselves: what can we do to help manufacturers stay ahead in these challenging times and switch this into an opportunity for them? To do this, our solution is automate repetitive workflows, empower decision-making, and add intelligence based on specified criteria. To see where this is going, we're going to launch into our first case study on components. Small parts that look modest compared to IP and fascia tools, but are deceivingly the most elegant. Mike Belanger has prepared this part of the presentation, so I'm going to pass over the control to him now. Take it away, Mike.
Thanks, Rob. As we start the automation, let's really consider the benefits and how you can leverage this type of automation in your daily workflow on smaller work pieces like this. Now, speaking from experience, I will be the first person to tell you that components can easily be the bottleneck in any manufacturing process. They are sometimes dismissed as they are smaller in size, but they often have complex details and usually need multiple setups to complete every facet, not to mention the drilling operations that could involve compound angles. So let's consider this. It takes you approximately 90 minutes to completely program a complex slide like I have on my screen here. And this could include the time it takes you for your programming, to set it up on a fixture plate, possibly creating some setup sheets for the operators to execute your plan, and getting your tooling ready for the job. Actually, 90 minutes may not even be enough time to complete all these tasks. But in this case, if the programming timing does take you the 90 minutes or more, and the actual runtime on the CNC machine is approximately 2 to 3 hours, you are barely making up any ground. And most machine shops nowadays are looking to see the benefits of unmanned machining, either after hours or with one programmer programming multiple machining centers. So, as an industry, how have we developed this problem? Well, in the past several years, we have seen tremendous advancements in regards to machine tools. They cut more accurately, much faster, and more commonly are multi-axis. Essentially, they can do the job much better and in a fraction of the time. So when we are working in a non-production environment, this puts a great amount of stress on the programming. With PowerMill's ability to customize your automation, we have taken component programming to the next level. Using a series of macros, templates, and the built-in automation, we can now address the entire slide in this setup. All rough cutting is completed in sequence, starting with the top setup, then tipping the slide on all four sides while using a shorter, more rigid tool so we can cut faster with less deviation. We are also using stock models to ensure that we are managing the remaining material in the most responsible way. You may have noticed this particular component has many flat surfaces around every side. The customization that we have written into PowerMill identifies each flat individually and addresses them in the most efficient way possible with a flat finishing toolpath. Notice that it does find all the flat areas, even those on non-common angles. This is particularly helpful as these toolpaths do not have a long runtime, but can be a bit more time consuming to create due to the numerous amount of angles required. Next, you will notice the 3D contoured surfaces with finishing toolpaths and corner finishing to complete the milling portion of this component. Now let's talk about everybody's favorite topic, the drilling required on these components. Honestly, I don't really have anything against drilling at all, but the thing that I always found to be troublesome was the fact that I was always seemingly working at a deficit in regards to programming time versus machine runtime. That should never be an issue again if you use the built-in drilling methods in PowerMill. And after building your drilling methods in the software, you can continue to use them for years to come. And the great part about this is that you build them to suit your needs. I made this particular drilling method for a regular slide component like this to address the water lines, the wear plate screws, and the spring pocket holes. But like I was saying, they can be built to suit your exact needs. As you see, with little to no effort, you can have all your drilling strategies completed and ready to be output to the machine. Now, obviously, all the toolpaths are editable, and additional toolpaths can easily be added for a particularly detailed area. But imagine this, you have 80 to 90% or more of your programming finished on these complex parts that are essentially a one-off. This time savings alone will pay for the software in no time, not to mention the stress alleviated for the programmer. Let's watch a quick time-lapsed rendering of the toolpaths running to get a real feel of what the end result will look like. I hope that in this segment, I was able to shine some light on what the struggles are when machining components, and more importantly, how to combat these issues in the most efficient way possible. By using PowerMill's built-in automation, you will have no problems reducing or completely removing the bottleneck that the average component department currently deals with.
Of our three cases today, this deep cavity block is by far the biggest in terms of size. The model file is a cavity half of a large fascia tool and requires the greatest elapsed calculation time. Because of this, we're going to split this portion into two parts. Jeff will kick off the automated process, and then we're going to circle around back to him after the calculation is completed. So for the intro to the cavity block, I pass the presentation on to Jeff.
Thank you for the introduction, Rob. And thanks again, everyone, for attending our presentation as we showcase the power of automation. Getting right in, we're going to look at how we can automate this deep cavity block. Now, this is a very large cavity measuring 98 inches in length, 38 inches in width, and 32 inches in height. We're going to want to first set this up on a boring mill for easy chip evacuation for the roughing. And when it's time to semi and finish, we're going to want to set up on a 3 or 5 axis machine. A couple other considerations for roughing are we're going to want to be using short tooling for the majority of the material removal, and if and when long tooling will be required to finish this process. Okay, now that we're in PowerMill, let's get our roughing automation started. With just a couple prompts, which I'm being prompted for what model I want to machine and what models I may want to consider as clamps. After these two prompts, the automation PowerMill starts running it in the background. And as we can see in the Explorer, toolpaths, tools, and items in the stock model are starting to populate. Now that we have this running, let's leave this and go and start looking at our considerations for semi-finishing. Now that we have our roughing automation starting and it's calculating, now let's look at our semi and finish operations. When this block comes back from stress relief, we're most likely going to want to throw it on a 3 or 5 axis machine. Can we set up automation to be used on the same block for multiple machine tools? And what would the smallest tool need to be used for finishing before we need to start looking at 5 axis toolpaths? Another consideration for finishing is what type of boundaries would we like to have in our automation to limit our toolpaths? And also, are we going to want to separate our model onto different levels to distinguish areas to simplify our machining? Now that we have some considerations, let's go and start our semi and finish automation. Now that we're inside PowerMill, you can see we have the cavity set up on a 5-axis machine. So now it's time to start looking at our semi and finishing operations. Now, with automation, you have options. We can fully automate the whole process where there's no user input at all, or if needed, the automation be set up so there's prompts for the user. In this case, I'm going to select the semi with prompts, and right away you'll start seeing that I'm being prompted for if I want to specify my smallest cutting tool diameter, if I want to use a boundary, and check for holder collisions. After I make my selections, again, we'll start seeing in the Explorer the toolpaths, tools, boundaries, and the stock model populating. Now that our semi-finishing and finishing is automated and running, let's pass this back over to Rob. Rob?
So, we are now on to my piece where I'm going to test the automation against a mid-sized core block. Now let's just jump right in. The core block dimensions in this example are approximately 900 by 600 by 300 millimeters. We're going to be using the same tooling as in Jeff's example, and similarly, I'll be using a horizontal boring mill for the roughing portion. Now, experienced programmers will have an ability to look at this job and visualize the workflow. They will pinpoint key considerations, such as using short, rigid tools as much as possible. For manufacturers to adopt automation, we need a solution that will respect this and solve many more deliberations. So, to interrogate the outcome of this automation, let us first highlight 5 fundamental considerations. The first being, can automation show preference for short, rigid tools? Is there a means for using longer tools of the same diameter only as needed? Will the tool paths using this smaller diameter tooling continue from where the larger tool left off? And in doing so, will this happen in a manner that carefully considers not just the model geometry, but also the current state of the stock? And naturally, we must also ensure that the entire tool assembly and machine components do not collide with any model, fixture, or clamp geometry. Now moving over to PowerMill and launching the automation, we're going to come up with just two simple prompts. One to select the machinable model, and the next to select the clamping models. Now each of those models will be respected in terms of collision, but obviously the machinable model is going to be specific to the toolpaths. At this moment, you'll see the PowerMill project start to populate with entities as it starts running its automation. Now this first part of the automation is fairly straightforward, so we're going to fast forward through this next bit. Now moving into a different session of PowerMill, we're going to get going on this semi-finish automation, and this is going to carry on where the roughing automation left off. We should note that the roughing automation concluded with green safety status on the NC program, meaning it was free of all tool assembly and machine tool component collision. Just as with the roughing automation now, there's going to be a few user prompts before it starts running all the automation sequences. To recap, enabling short tools to machine the maximum amount of stock is a straightforward task. And also we've seen that long tools will only be used as needed. Now in the event that a long tool is unnecessary, you can dictate whether you wish the unnecessary toolpath to be removed from the project completely or dropped in a rejected folder for the user's verification. In this example, we can see that there are two toolpaths, one uncalculated, one calculated, that have been moved to a folder called rejected. What's interesting about this, the uncalculated toolpath is obviously an empty entity, but the second toolpath with the blue check mark is in fact calculated. The difference in this example is the toolpath that was calculated was very tiny, in fact not even worth running. Perhaps it would have only run for about 5 seconds. Clearly not worth adding to your NC program. PowerMill does have the tools to interrogate this and deem a toolpath unnecessary. Moving on to our third consideration regarding tooling diameter. This was straightforward as well, but the key takeaway is knowing that this was done efficiently with stock management. This, along with the security of knowing that the true state of the stock is considered while entering and exiting the toolpath segments. And of course, your clamps and fixtures can now rest easy too. This green check mark verifies that they will no longer be assaulted by the tool, holder, spindle, machine component, or otherwise. With the automation wrapping up, I'm expecting to see a little informational window pop up. There we go. Along with a long list of toolpaths, including non-90-degree flats, and an NC program with complete green lights. Fantastic. With the slide component complete, and now the core block as well, all we have left is to wrap up the case study on the large cavity block. I'll pass it on back to Jeff.
Thanks again, Rob. Let's head back into PowerMill and check our roughing operations. Okay, so the automation is finished running, and we could say we have 5 roughing tool paths, all with blue safety lights, which is telling us that they're gouge and collision free. Let's look at the model for a moment. And as I toggle the shading on and off, you can see exactly the remainder of the stock, which is a good visual letting us know if it's ready for stress relief or not. Okay, so let's look at what we've just seen in PowerMill. All our roughing toolpaths are calculated, showing blue safety lights, which is telling us that these are gouge and collision free. This stock model is also now ready to be used for our finishing setup. Now that we're happy with our roughing, let's go take a look at what our assembly looks like. All right, let's take a look at our finishing operations. Again, we can see our toolpaths have blue safety lights. Also, we can see that all our toolpaths have been added to an NC program, which have been verified for collisions with our machine tool, showing all our green lights. We also see a warning light, which is telling the user that machine tool is within the clearance value, which is also built into the automation. And again, we have a nice, easy visual reference to determine when 5-axis machining is required.
At this moment, I suspect we have shown everyone that complex multi-axis automation is not only doable, but it can be optimized to make decisions specific to your needs. So, now we're on to the second half of our presentation and shifting focus onto the macro script itself. Jeff and Mike will help programmers new to macros find their ground, and then I will continue on to highlight some of the tips and tricks that we have learned in building this automation. But before I hand it off to Jeff and Mike, I'd first like to answer the question, what is a macro? A macro is simply a file that contains a sequence of commands that we can use to automate a series of operations. The graphic here is depicting use of the type command drawBlock and undrawBlock. And if these lines of text were saved as a macro, PowerMill would execute them sequentially. Now, admittedly, it is easier to build macros when you're familiar with the script, but this is by no means a requirement for capturing a good portion of your daily mouse miles. And getting started cannot be easier. I'm going to pass it over to Jeff Stelling and Mike Belanger for a couple of quick reveals on this simplicity.
For this example, I will create a macro that will calculate our block and then calculate our safe heights. I've previously created a folder on my desktop where I will be saving my macro. To start, I will go under the Home tab, go to the right area here under Macro, and select Record. This is now prompting me where I want to save my macro, so I'll find that folder, and I will give my macro a name. As soon as I hit save, PowerMill will begin to record every click within this session. Now that we're recording, I'm just going to run through the steps, calculate my block, go under the toolpath connections, calculate my safe area, and hit accept. Now that we've done that, I'm going to go back under the macro tab and hit record to stop recording. Now I'm going to go under the Explorer, and under the macro pull-down menu, I will find the macro that I've just recorded. To ensure it's correct, I'm just going to go reset my safe heights to 0 and delete this block. Now I'll just right click on the macro, select run, and as you can see, the block is calculated and my safe area heights are calculated.
So, in this segment, I will be discussing how to create tool templates of your favorite tools and then how to import them with the click of a button from your custom tab. Many users have a tool library that they pull tools from on a daily basis that represents actual tools that they have in their carousel. But often these tools can get a bit cluttered and be a lot to sift through. So what I've done in the past is actually pull my favorite tools from the library for a specific operation. As you can see, I've pulled in 10 of my favorite tools here and save them off into a template. Now, it's very important to remember that when you are saving a template, you need to have a fresh session of PowerMill open to do this, because when you save this template, it will pull in any other entity that you have in PowerMill. So if you have a boundary, pattern, work plane, anything, it's going to save it along with the template. So in this example, as you can see, I only have a list of tools here. I will go up to my File tab, which is the Backstage area. I will choose to Save as Template Object. Now, this template object is going to be saved into a folder on your computer or possibly on a server somewhere that you know your files will be safe from being deleted. There we go. Simple as that. I have the tool template saved. Now, if I delete this, close my session of PowerMill, sure, it's very easy to import template objects, and then from that folder, once I search to it on my computer, double click, and then import my tools. As you can see, the list just came in right here. But I want it to be just a little bit easier by creating a macro and having that macro pull the template in with the simple one click of a button. So let's start over here. I'm going to start by recording my macro. I will save this as whatever name I choose. Once I hit save, the macro starts recording. I will very simply import template object, grab my tool template, and have it imported. Click the record button again to finish the recording of the macro, and we can see we have our tools there. Once again, I'm going to delete those tools and jump into my custom ribbon. With my custom ribbon open, I will go to my favorites tab, create a group, and in that group, I am going to create a macro button. Okay, search to the macro wherever it's saved, right here. And if you wish, you can assign an icon to it as well, either one of the stock ones or a custom icon if you wish. Okay, I'll just choose this icon for right now. Once I add that button to my new group and click OK, you can see I have no tools in my Tool Explorer right now. When I go to my tab and click that button, I simply have all of my tools imported that I wish.
Very good. Thank you, gentlemen. Returning to our tips and tricks on macros, let us look at the actual macro text. This looping clip offers a visualization of how the code is read line by line. Now, looking at this still snapshot, take a moment to appreciate the friendliness of this layout. This is my first suggestion for all of your macros. Take the extra bit of time to label each group of lines, and cluster these lines as relatively small groups if possible, that perform manageable sections of the puzzle. It is also especially useful to space these groupings by 3 lines or so. This way, months down the road, if you need to edit the macro or find a particular function, you can simply scroll group by group, and it'll be obvious where one function ends and the next begins. Of course, if the group is titled, you may more easily search by name. With groupings in mind, the next 5 slides will dissect a couple fundamental processes, much like we did for our toolpath considerations. Our first question: how do we verify that the automation will find all of the project entities that it requires? Second, how do we eliminate user messages and other disruptive prompts to allow the automation to run without interruption? Third, and a very important one, how do you build an automation that is capable of handling errors? And, if desired, how do you allow for some user-defined input? And of course, one of the most important pieces as well, how can the automation handle situations such as these 2 surfaces that are flat but not normal to a 3-axis machine tool? The solutions. Here is a block of macro lines that searches the project for specific entities. Now, we have found that we most often require a project to have a predefined machining datum. To verify that one exists, you can simply create an entity list of all the work planes in your PowerMill project and return an error if that list is empty. An alternative would simply be checking for an active work plane. In either case, you can go a few directions at this crossroad. such as automatically create a datum at the bottom center of the block, or pause the macro while the user interacts with PowerMill, or in this example here, simply cancel the macro while returning a message to the operator. Regarding unnecessary prompts or disruptive prompts, here's a sample of some lines we often use near the onset of a macro. Naturally, you want to be selective with which lines you add or omit, but this is a good start to an automation for which you want no existing project entities to be considered. Also, by switching warning and message dialogues off, you can avoid those interruptions to the calculation. Overcoming errors is a very important step in building a successful automation. Here is a very simple do-while function that adds a counter to a string. The purpose of this function is to first ask PowerMill if the name of an item you plan to create already exists. If PowerMill says yes, this name is taken, then a number will simply be added to that string. This helps you overcome the issue of explicitly defining your workplane name as datum or G54. With no sensitivity to name checking, your automation will be prone to failing. Allowing for user input is a critical piece of the overall success of your automation as well. Now, this may sound in contrast to the efforts of full process automation, but the reality is this enhances the user experience, so long as you do not overdo this. For example, we mentioned that we often write automation that requires an active workplane. Now, what if you run this automation before activating the workplane? Perhaps you forgot. Eventually, the automation will be at an impasse, and if you don't build sensitivity into this, the automation will fail and essentially have wasted the user's time. Instead, perhaps a macro can pause and allow some user interaction, or offer an entity list, a list of workplanes, and then the user would select which workplane do you want to activate before continuing. Little finishing touches like this enhance the experience and keep the automation running smoothly. Some other very popular prompts include the ability for a user to select an item or multiple items from a list. This group is titled User Input to Enable Optional Add-ons. Executing these lines will offer the user options to add to their automation. Please note that Input Choice Multiple allows for multiple selections, where Input Choice only offers single selection. Now, the script for these next two coming up in just a moment are quite a bit different than this one on our screen. And this is because our first one here is a string list. And a string list is merely a list of alphanumerics that have no actual project entities associated to them. It is also notable that items in this string list are referenced by the integer with respect to its position in the list. Let us now look at an entity list, which is quite a bit more concise. Items in this list are directly associated with the project entity. How this may be useful is allowing a user to select specific toolpaths from the project to perhaps collision check, apply boundaries, or run any other sequence of commands defined within the curly brackets. And now the fifth piece, a very simple yet very important piece of the puzzle. How do we include some bit of decision making? Adding sensitivity to the active machine tool in your project is a possibility. Now, these lines are not elegant, but they do offer the ability to import correct tooling and machining templates based on your active machine tool in PowerMill. It essentially reads like this. Number one, if the DoSum machine tool is active, load its particular tools and machining templates. Otherwise, number two, if the 5-axis Celca is active, load its tools and machining templates. Otherwise, just bring in my generic tools because I'm not yet sure which machine tool I'm going to operate. In summary, templates and macros will allow programmers to capture the repeatable processes. Experienced programmers can find themselves increasing their output dramatically. However, this approach does not necessarily standardize your workflow. By escalating into full process automation, you gain additional time savings, completely standardize your programming practices, and allow new users to program confidently and nearly as efficiently. Automation can help bridge the skills gap and address the skilled labor shortage. Imagine nearly all of your finished programming being captured in a reliable, robust, and standardized manner. Successfully implementing full process automation in your finishing department can offer you tremendous time savings and offer you the confidence that all users will be executing the same practices. But perhaps greater than savings is peace of mind. Dramatically reduce your concerns of workplace burnout. Automating your CAM solution will enable flexibility, control costs, and overcome the challenges of tight timelines on key programmers.
Thank you for taking the time to join us today. I hope you gained further appreciation for the power of automation and helped identify where it can enhance your manufacturing process. We're now at the Q&A portion of today's presentation, and our team would be happy to answer your questions.